welcome to lecture 2.3 of this course. It's the third and final module of unit 2, which is on basic definitions and concepts. So in this module, we will review concepts pertaining to signal representations, complex numbers, dot products, and projections, and conclude with a quick review of the linear independence and what's known as a basis. Now, these are actually essential at various points in the course. When we apply these concepts, you'll realize the importance of whether it's of these points that we are going to review today. So the first topic of interest to us in this module is the signal representation, because the entire analysis is based on how we represent the signal. That's a very important point to keep in mind. Whenever we are analyzing a signal, behind the scenes is a signal representation that's working for you. Depending on how you represent the signal will be your analysis. We are particularly interested in periodic signals. Of course, you may ask, what about aperiodic signals? Well, aperiodic signals can be in turn expressed as a weighted combination of periodic signals. That's the basic idea in Fourier transforms as well. So we'll start with periodic signals. If I have a periodic signal with a single frequency, then I can write it as that I've shown in equation 1 here, x of t as a cosine omega t. It's a continuous time periodic signal. A is said to be the amplitude and omega is said to be the frequency. Of course, omega is it's the angular frequency. The cyclic frequency would be dividing by 2 pi. Now, a quick note on this amplitude. This amplitude is not the value of the signal at any point in time. It's rather the maximum or the minimum. Essentially, it's the magnitude of the extrema of x. So you can imagine the periodic signal as a constant riding on a cosine or a sine wave. It could be sine as well. So that's the basic signal representation. Of course, not all periodic signals can be represented with a single expression. But that's the idea in Fourier series. If I have another periodic signal, I could express that another periodic signal in terms of these cosines and sines and so on. When the amplitude itself, that is the extrema itself, is changing with time, then we say that there is an amplitude modulation. Further, we can bring about a phase modulation. Now, what is phase here? Loosely speaking, phase is the product of omega times t here. This phase is different from the phase lag that we normally use. So you should not get confused between these two. So whenever I have an amplitude modulation and phase modulation, I have the expression here in equation 2. It's natural generalization of the representation in 1. We can further generalize this to obtain what is known as a complex representation of a signal. So equations 1 and 2 are for real valued signals. What if I choose to have a generalized representation such as the one in equation 3? The question that comes to mind is, why do I need a complex representation when the signals that I'm dealing in real life are actually real value? But we will answer this question at a later time when we speak of so-called analytic signals. Remember, we are talking of signal representation. Whenever we talk of signal representation, all that we are looking at is how to represent the bunch of numbers that I have in the signal. And there are numerous ways of doing it. The complex representation is particularly useful in time frequency analysis, particularly in the evaluation of so-called instantaneous frequency, as we'll learn later on. So we will not really dwell into this so-called generalized or complex representation of a real valued signal. In the signal representation, now we have come across this complex numbers and so on, and we will encounter these complex numbers very frequently in Fourier analysis. So a quick roundup of complex number theory. Complex number is nothing but a point in the two-dimensional complex plane where the horizontal axis is conventionally the real part of the complex number and the vertical one is the imaginary one. So fairly straightforward. The of particular importance is the polar representation of the complex number, where we rewrite the complex number in terms of what is known as a magnitude and a phase or an argument or an angle and so on. So there is a relation, one-on-one relation between the magnitude and the phase and the real and imaginary portions, as I have shown in the schematic here. R is the amplitude, it is the magnitude of the complex number, and theta is the phase or the argument of the complex number. In complex number, in the analysis of complex numbers, we often encounter what is known as a complex conjugate. That's fairly straightforward to understand. The sign of the imaginary part is reversed, and therefore I can write the z star. There is a small mistake here. It should be r e to the minus j theta. I'll correct that for you. And the real and imaginary parts of the complex number can be rewritten in terms of the number and its conjugate itself. Likewise, the magnitude can be expressed as a product of square root of the product of z and z star, and the phase of the argument is nothing but the tan inverse of the imaginary over real part of the complex number. So these are the basic concepts that one should be familiar with in dealing with the transforms. Now moving on, one of the key linear algebra operations that we would be involved in signal analysis. Remember, we are performing operations on signals when we are analyzing them. So one of the key operations that we'll be performing is what is known as a dot product, and this is a fundamental operation that one would encounter in all signal analysis. We learn this in high school mathematics. The dot product dot product of two real valued vectors v and w, we say that they are in the n dimensional Euclidean space, is defined as shown in equation 4 here. It's nothing but the element wise product and summation of those element wise products of the two vectors. Obviously they have to be both of the same dimension. You could interchange the order of the inner product, so it's not sensitive to the order. However, if v and w are complex valued, the ordering matters, as we will see shortly. Now the dot product is a special case of what is known as an inner product in vector algebra or linear algebra, which is denoted by this left and right angular brackets, and the length of a vector denoted by this norm here, these double dashed lines, is nothing but the square root of the dot product of the vector with itself, and the dot product is also the squared 2 norm of the vector itself. Okay, so these are some of the useful relations, and in MATLAB you can compute the dot product between two vectors using the dot command. Now further insights into the dot product. Earlier we saw linear algebra perspective. Now the geometrical definition of the dot product can also be obtained. You can show that the dot product is nothing but the magnitude of v times magnitude of w, that is the length of v times length of w times cosine theta. That gives us also a definition of the angle between two vectors in terms of the dot product. Clearly from this result, if these two vectors are orthogonal, then cosine theta is 0. Naturally, then the inner product is 0. So that's a quick check for orthogonality of two vectors, and in fact it also constitutes a definition of orthogonality. And the standard Schwarz inequality on the dot product, we will use this at some point in time. In fact, we'll use this in probably deriving the duration bandwidth principle at a later time. And for complex valued vectors, the ordering matters, as I mentioned earlier, but the rest of the operation is the same. The key difference is, instead of taking the transpose, we take what is known as the complex conjugate transpose, also known as the Hermitian of the vector. And scalar number that comes out of this dot product operation can be complex valued. Therefore, in evaluating the angles between these complex vectors, we only use a real portion of it. So that's the prime difference now between the dot product of real numbers and complex valued vectors and real valued vectors. Okay. So as I said, the dot product is a generalization of an inner product, and very often we will work with inner products. Whenever I'm looking at a signal transform, whether it's Fourier transform or wavelet transform and so on, I work with express the signal as a linear combination of some basis functions or analyzing functions and so on. The coefficients of these expansions, it turns out, are evaluated by first evaluating the inner product between the signal and the analyzing function itself. You will see this in module 3.1. So the inner product between two vectors is a product that has to satisfy these properties known as conjugate symmetry. Conjugate because we want to take into account complex valued vectors. Positive definiteness, which means the inner product of a vector with itself can be non-negative, and if it is 0, then it can only occur under trivial conditions, and it has to satisfy linearity. So although I say linearity in the first argument, it has to actually be linear in both arguments, but if you bring in the conjugate symmetry into picture, you can show that it will also be linear in the second argument. Now it's easy to verify that the dot product satisfies all the above properties and therefore is one of the possible inner products. You can actually define an inner product that is not a dot product, and I've given an example here. I leave it to you to verify that this indeed satisfies all the three properties here. The inner product between two functions, remember there is a difference between vectors and functions. Functions are defined here, functions are defined over a continuum, and therefore you can think of these functions as infinite dimensional vectors. If these functions are in the Hilbert space, which means there is an inner product that's defined and there is a finite norm that is induced by the inner product, that also exists, and certain other properties satisfied. I recommend you to look up a book on linear algebra that talks about Hilbert spaces. If these two functions live in the Hilbert space, then the inner product is defined in this fashion, and we will keep using this inner product many times. If you recall, I had defined a continuous time wavelet transform for the continuous time wavelet transform for you in the introductory lecture, and you can relate f is taken by the signal, the role of f is taken by the signal, and the g is replaced by the wavelet itself. So the continuous wavelet transform can be viewed as an inner product between the signal and the wavelet itself. Although dot products are special cases of inner products, we will use these two terms interchangeably. Okay. So whenever we say inner product, unless otherwise specified, we mean dot product and so on. So moving on to projections. So we have defined what's a dot product and what's an inner product, and now we want to move on to projections. Now the projection is a very important concept in signal analysis, because projections are nothing but approximations, as I will explain to you shortly. In fact, all transforms can be viewed as projections of the signal onto the analyzing function or the basis function. All right. So there are different kinds of projections that are possible. You can have orthogonal projection, you can have an oblique projection. Very often we work with orthogonal projection, but there are of course many situations where oblique projections are involved. So let's understand what's the orthogonal projection. Let's take a look at the schematic that I show here on the left. There is a vector v, and I'm projecting this vector v onto the vector w, and I have indicated here this distance here, this length, as being the orthogonal projection of v onto w. All right. Now what we are doing here is we are dropping a perpendicular from v, from where the arrow ends, and onto w, so that it's perpendicular to w, and therefore it is called the orthogonal projection. The other term for projection is shadow. When we walk on the road in daylight or sometimes even in any light, we see our shadow on the road. That's a projection of the three-dimensional body onto the two-dimensional plane, which is the road, right? So here I'm projecting v onto w. I can also project w onto v. Nothing prevents me from doing that. Now this is called the orthogonal projection because simply I'm dropping a perpendicular here. I might as well draw any line from the arrow of v, the head of v, onto the w. Then it becomes an oblique projection. I will show that to you on the board. So when I have a vector v like I have on the schematic, and this is the w here, right, then right now I have a perpendicular dropping from here, and this is called the orthogonal, this length is called the orthogonal projection. But I could draw many lines this way, and each at a certain angle, right. So, there is a certain angle to all of this. We call all these other projections as oblique projections. And these oblique projections are defined with respect to another vector that's running parallel to this. So, the oblique projections will also involve what is known as a third vector, but we don't define that here. Now, the scalar projection can also be given a vector interpretation by saying that this is nothing but another vector in the direction of w, and that becomes a vector projection. So, the only difference between the scalar projection and the vector projection is that there is no direction to this number, it is a number, but here there is a direction to this number, clearly indicating it is in the direction of w, all right. And that is the reason you see in the vector projection there is a multiplication with w by its own magnitude. So, you are essentially multiplying this number with a unit vector in the direction of w. So, that is why it is called a scalar and a vector projection, and so otherwise these two schematics look alike. Now, a very interesting property of this orthogonal projection is that it is the best approximation of v using w. So, if I want to express v using w, then the scalar, the orthogonal projection offers the best projection in the minimum mean square error sense. In other words, by if I look at this vector projection here, this is the error. So, vectorially if I call this as E and this as the orthogonal projection, let us call this as v hat, I can write therefore vectorially as v being v hat plus E. So, this is the error that I am making in approximating, if I approximate v with v hat, this is the error that I am making. For all other projections will give me the a larger magnitude of E, and that should be fairly obvious if I look at this, and this is also the so called least squares solution or least minimum mean square error approximation of V using W. Okay. So, that is the most important property of the orthogonal projection, and now you can understand why projections and approximations are very closely related. We will use this concept of projections time and again in Fourier transforms and wavelet transforms and so on. So, we will conclude this module with the concepts of linear independence and basis, because we will need this when we talk of DWTs and so on. The concept is fairly straightforward. A set of vectors is said to be linearly independent if and only if their linear combination is 0 under trivial conditions. Okay, that means, so what is a linear combination? This is a linear combination. If this is 0 only under trivial conditions, then we say it linearly independent, which means if it is 0 under non-trivial conditions, which means I can find non-zero constants that will result in a zero valued linear combination, then we say that the vectors are linearly dependent. And what linear dependence naturally means is that one vector can be expressed as the combination of others. So, let me give you an example of set of linearly independent vectors. So, if I look at these vectors here 2 and 5, so this is v1 and this is v2, then these two vectors are linearly independent, because simply I cannot express one as a scalar multiple of the other. Okay. The other way of saying it is I cannot find a non-trivial solution to this equation. All right. On the other hand, if this was 1 1 and 2 2, then it is obvious that v2 and v1 are linearly dependent. So, that is the basic idea. Now, a quick note on the connection between linear independence and orthogonality. So, earlier we had this vector and we showed we realized that these two vectors are linearly independent, but that does not mean that they are orthogonal. Very often it is confused. what is the way to check orthogonality? I compute the dot product, and if it turns out to be 0, then I say that they are actually orthogonal. So the dot product between these two vectors is 1 times 2 plus 1 times 5, and that comes out to be 7, which is not 0, and therefore it is not orthogonal. On the other hand, all orthogonal vectors are linearly independent, and that I will leave it to you to check. All right. There is a special feature of that is a special feature of this orthogonality, and orthogonality is desirable in compact representation, signal compression, and so on. So finally, we talk of span and basis. Span of a set of vectors is nothing but the linear combination. So we saw the linear combinations in the context of linear independence. Now we are talking of basis. A set of vectors is said to be the basis for a vector space W. Whatever that vector space is just a matter of notation. If two conditions are satisfied, the vectors are linearly independent, which means as Gilbert-Strang puts it, don't have too many vectors. What we mean by basis is how many basic elements you require to express all the vectors in the vector space. So if you have too many, more than required, then that means that you will bring about a linear dependence between them. So you don't want that, and you don't want too few, which means if you choose fewer than required, then you will not be able to span the entire space. What we mean by span is to be able to generate all possible combinations, right? So the classic, if you take the two-dimensional real space, the classic set of bases are 1, 0 and 0, 1. So those are the two different basis vectors that we normally are given as examples, 1, 0 and 0, 1. But I might as well choose these two as the basis for the two-dimensional real number space, because this also can span the entire two-dimensional space. They are linearly independent. The only difference between these two is that this is orthogonal and this is linearly independent. So since orthogonal basis vectors are also linearly independent, basis admits orthogonal basis. In fact, orthogonal basis is a highly desirable feature, as I said earlier, in signal compression and so on. And finally, the number of vectors in the basis set for a vector space is said to be its dimension. So these are the basic concepts that we'll require before we move on to the world of Fourier transforms, wavelet transforms, and so on. I would suggest that you make a good reading of the book, particularly by Gilbert-Strang, because it gives you very nice ideas on, very nice insights into linear algebra. It's an excellent book, very renowned book. Please go through some additional reading before you jump to the next unit. Thank you.